Hi, this is Tom Fitteman with Ventana Systems, and today I'm going to walk through the process of analyzing or critiquing a model in vensim. So we'll take a look at why we want to analyze things in the first place, some good habits for working with models in general, and then look at the process of taking apart a model. We're going to focus on global models because that's something that's of interest to everybody since we all live in the same world. And there's also an interesting family of global models that's grown up over the last 4 decades or so. We'll focus primarily on world dynamics, but also provide the materials for World 3 Wonderland and the DICE model, and these are available in the vensim video library. So, why bother analyzing models at all? Well, I actually find it intrinsically interesting and fun, but really the bottom line is making better decisions. And we get there by having a deeper understanding of the model, by avoiding misuse of the model, applying it in situations where the assumptions behind it really aren't appropriate. And a bit counterintuitively, it's actually faster to build models by deeply analyzing them as you go. That on the surface doesn't seem right because the analysis process takes time, but if you do that, you'll avoid a lot of costly mistakes that trigger endless rework cycles. So, really, doing high quality work through extensive analysis as you go is the fastest way to get done. The analysis process really breaks down into four major steps. First is identifying the problem that the model is trying to answer and for whom, and other circumstances of its intended use. Without that, you don't know how to judge decisions about aggregation and what's in and what's out, for example. If you don't have the model in hand, then you need to replicate it in some way so that you can actually run it and work with it. If you can't do that, you can still do structure inspection, which means just looking at the equations and larger structures of the model to understand their purpose and the information used in decisions and so forth. But really, actually, the faster route to structural understanding is through behavioral testing, doing sensitivity analysis and extreme conditions tests and so forth on the model, because actually that behavior testing will very quickly reveal structural defects or interesting features of the model behavior and their structural origins. While you're engaged in this process or in model building in general, there are some habits that will really help you. One is to just follow the scientific method, do controlled experiments on the model, change one thing at a time. There's a role for multivariate experiments as well, but often that's harder to interpret. So you don't want to fall into the trap of varying two things and then attributing the result to the wrong one of those two. That's the key. Another is to keep a lab notebook of what you're doing and record your expectations every time you do an experiment. The human mind's power to rationalize almost any crazy behavior from a model is surprisingly large. But if you capture your expectations beforehand, then you have the opportunity to be surprised, and you'll either learn something about the model or you'll learn something about your mental model. The goal here is really to relate the behavior of the model to its structure and understand all aspects of that. And in particular, you want to be thinking about the big picture of the structure of the model. The defects may be down in the weeds in individual equations, but there's also always the question of what is this model really doing and what are the big feedback loops that are driving the behavior. Part of that process is actually looking at everything in the model at some point. Obviously, if a model has thousands or millions of variables, you can't really do that, but you at least want to hit all the key states. And then finally, the model analysis process works better if you do it with colleagues. Share your insights and discoveries and discuss them, and you'll learn a lot more. By way of background, here's a quick family history of global models. There are really three main traditions coming from the system science world, the economics world, and the natural sciences world. In the systems world, things really kicked off with world dynamics and World 3 in the early 70s. In economics, it started with growth models like the Ramsey and Solow models. Today, it's much more driven by big, detailed computational general equilibrium models. And then in the natural sciences, people have been working on models of the planet, planetary nutrient cycles and carbon cycle and atmospheric processes for a number of decades as well. And then there's some spillover. So, for example, the hybrid of the natural science and economic traditions is in the climate integrated assessment models. World Dynamics was published by J. Forrester in 1971, and that's the one we'll spend most of our time on here. So, if you're picking up the model, which we'll do in a moment here, the first thing to do is just browse through it, see what's there, what the decisions are, what the stocks and flows are, and whether you see any familiar structures or possible problem areas. Another thing that's easy to do right off the bat is check the units. If there are errors or there just aren't any, that's right away a red flag. So here's the world model. This is based on the original Forrester version with a few interface upgrades. So first thing, I'll check the units. They're okay. So let's take a look around. You'll notice some navigation buttons, or you can use the menu here to scroll through the model. So first up is the population and food sector. So pretty familiar stock of people with births and deaths. And then a lot of drivers on those: food, pollution, material, etc., both on the birth rate and on the death rate. And you'll notice we have some graphs over here so that we can see what things are doing. If we continue down to the capital sector, again, just a simple stock of capital and a sort of a quasi-coflow for the fraction of capital that's devoted to agriculture. Here we also have a quality of life metric that's a function of crowding, food, pollution, and material possessions or material output. If we continue down, we have a stock of pollution, increased by generating pollution and taken up by natural absorption processes. And we have a stock of natural resources that gets used up in the course of producing industrial output. Then we have a couple of control panels. So this one's designed to essentially let us see all of the states of the model. So we've got population, capital, resources, pollution, and the capital agriculture fraction. It's nice that this is a small enough model to be able to do this. And then we have all of the parameters. So when we turn this model on in Synthesim in a moment, we'll be able to play around with everything at once. There's also a set of kind of the qualitative multipliers. So we have the output quality of life, and then the crowding, food, and material standard of living inputs to that, and some parameters for those relationships. And then a particular control panel that's targeted at finding, if we can, equilibria for the model. We'll use that again in a moment. And then finally a phase plot for the population-pollution relationship, as well as the behavior over time of those two states. So let's get back to the structure view and see what we can learn about this model. Now I find the first thing I want is a base run that can be used as a reference so that I can detect the difference between an experiment and the original behavior of the model. So I'm just going to hit simulate here to generate a base run. And then I'm going to change the run name to test. So all my experiments will be in a separate output data set. And I'll turn the model on using vensim so that I get sliders on all the parameters. So what do we want to know here? Well, basically it's helpful to just play around at first and figure out what the model does, what does the behavior mode look like, and then play around with some of the parameters, see if you can get different behavior modes out of it, and start trying to understand how this behavior originates from the structure, from the feedback loops, and also determine whether it's endogenous or whether it's driven entirely by external disturbances like driving data. In world dynamics, of course, there isn't any driving data, so we know off the bat that the behavior is endogenous. One thing that's helpful to know right off the bat is whether the behavior is real or an artifact of the simulation method, and one good way to test that is by varying the time step. So I'm going to change the time step parameter. You can also do this when the model is not running in the model menu in the settings dialog. But I'm just going to do it on the fly in vensim here. So you see that this model's running for 200 years. So it runs till 2100, starts in 1900, and with a time step of a quarter of a year. So what happens if I make that half as big? So an eighth of a year, 0.125. Now you'll notice the behavior is essentially identical. That's a good thing. That means that this is essentially not a factor. I suppose for safety, I ought to go ahead and take a look at our control panel here to make sure that nothing else changed. So here we're looking at all the model states. So if the states haven't changed, we know that nothing else has changed. So that's good. What if we make time step big? Let's say we make it 2 years. What happens? Okay, so this is the kind of thing you might see if you had a model that was generating behavior as an artifact of some kind of instability. So if you look at the pollution graph here, you'll see that it's oscillating wildly. So we could go and look at the pollution sector. And actually just by eyeball here, if you look at generation, that's not really participating in the oscillation, but pollution absorption clearly is. And as is the pollution ratio and the absorption time. So if we look at the pollution absorption time, the bigger graph, what you can see is that this is a time constant of quite a bit less than 2 years. So it's not surprising that this has gone unstable. Also thinking more broadly about what this means that the pollution uptake process is actually pretty strong if pollutants are removed with an average time constant of under 2 years. That's a far cry from things like carbon dioxide that have an atmospheric lifetime of a century, or methane, which is a decade, or some of the fluorocarbons that could be millennia. So that's an interesting piece of information about the model as well. To get back to a clean slate, I can either just stop vensim and restart it, or I can hit the reset all button here. And that brings my pollution parameters back to their original state. Now if I want to understand a little more about pollution, I can start playing around with this structure in isolation. And you'll notice that the only influence impinging on it is through the pollution generation process. So if I want to cut this sector off from the rest of the model and understand how it behaves, I can replace pollution generation with a constant. In some versions of vensim, you can use what's called an override, which is by far the easiest way to do this. I can just right-click this variable while synthesim is running and set it to be a constant, and I'll run it from 0 to 40 billion. And I'll set my slider to 20 billion, and these are abstract units of pollution. So now my pollution generation is just a constant. And actually, you'll notice the yellow warning bar here is indicating that I've triggered a floating point error. But pollution is rising rather dramatically over time. So what I should probably do is stop and take a look at the origin of that error. I've clearly discovered a limitation of one of the formulations in the model. Looks like it may be in part related to the natural resources. That looks like a problem. But it's also interesting what's going on in the pollution sector itself. As pollution rises to a very high level, as you can see in the graph here, what you'll notice is that the pollution absorption time, which was formerly under a couple of years, has gone up dramatically and saturated at 20 years. So what that might mean in the real world is, and of course you could refer to the book to see what the explanation is sort of a poisoning of the, or saturation of the natural uptake processes that are responsible for restoring pollution. So as those sinks get saturated, the time constant for further uptake becomes dramatically longer. So that's a reinforcing feedback on pollution. So we should go and investigate what's happening here, but I won't do it in the interest of time. So let's tone down the input a little bit. So I'll go down to 10 billion units. Now you'll notice pollution has the kind of equilibrium behavior you typically expect, which is a exponential approach to a goal. And that's because the absorption time is remaining relatively constant, under 2 years, and we're not triggering that runaway positive feedback. So clearly the pollution system in the model has a kind of a threshold behavior that can be triggered by extreme pollution scenarios. So that's another interesting piece of information about the structure and behavior of this model. On second thought, I probably shouldn't be so dismissive of this floating point error that we are seeing. So let's put the population back. Notice at the onset there around 16 or 15 billion. We'll put the pollution back to 20 billion units. So we're getting an error. So where's that coming from? I noticed that the natural resource material there, the natural material multiplier was behaving a bit strangely here. So let's use the causes strip graph tool to track that down. So there's the lookup, and let's close this other graph. So we're tracing this back. So there's the multiplier, there's its input material standard of living. That goes negative. That's never a good sign for something that ought to be a physical quantity. So we'll track that back. So that depends on capital ratio, that also goes negative. We'll keep tracing back. Okay, so that depends on capital agriculture fraction. So a little weird that that's saturating at 1. It means all capital is devoted to agriculture. But the thing that's really going haywire here is the capital ratio, going to 10 to the 38th. Not likely a sensible number, so let's keep following that. And this may be the problem. If you look at the capital ratio as capital per capita, and we don't have any per capitas left because we've killed everybody with pollution. So let's go back up and look at the population sector. So you can see people have a high death rate both because of food and, more importantly, because of pollution. So one thing we could do is just turn off this sector temporarily to try and understand what else is involved. So the whole issue may be that the capital ratio is not robust to near zero population. That actually seems pretty likely. But let's test that by overriding the population with a constant. So I'm just going to right click, set that to 2.5 billion people constant, so you can see that that's kind of a vaguely typical value over a normal simulation, or over the base simulation anyway. And then let's see what happens. So you'll notice that that got rid of the floating point error, and pollution now rises to an equilibrium, except that it's still a very high equilibrium because of this phenomenon of the absorption time becoming very long. You also notice that natural resources no longer get depleted because everyone's dead, and the economy is essentially shut down if you look at the capital stock, although you'll notice capital drains away more slowly than people. That may be an issue as well. So I think we have at least a beginning of a handle on the mystery of the floating point error. So we've gotten the whole model we've gotten the pollution sector into equilibrium, but we don't have the whole model in equilibrium, although actually the resources are coming into equilibrium as well. But it's interesting to think about what's the equilibrium of the whole model, and is there even an equilibrium? This is a more appropriate question for some kinds of models than others. In, say, a supply chain, it's reasonable to assume that the whole supply chain's inventory and order levels could come into an equilibrium because demand was essentially stationary. In a growth model like this, it may not be reasonable to think that there is some kind of equilibrium. But in any case, it actually is not too important whether there is or isn't one, because the process of looking for it may reveal some additional insights about the behavior. So let's do that, and I'm just going to stop the model to get rid of all our overrides and any other changes I might have made and forgotten about. Start it up again, so we're back to the base case, and I'll move down to the equilibrium control panel. So this is just a picture of the 5 states in the model, plus a slider for the initial condition for each of those states. And I could just start playing around to see if I can find an equilibrium manually here. And in a second order model, or maybe in a model with less of a growth trend to it, that might actually be practical. But here it's looking pretty tough to get it into equilibrium. Although it's quite interesting that as we play around with the initial state of the model, we're seeing quite a few different sets of dynamics here. And we're also getting a sense that some things matter more than others. So, for example, changes in the capital fraction to agriculture seem to work themselves out rather quickly without any lasting changes on the trajectory. Same is true of the initial pollution state. Pollution quickly gets restored to whatever it was going to do anyway, but on the other hand, natural resources matter. In fact, look at the oscillation emerging in pollution as I make resources very large. And the initial population seems to matter, although now I've restored it and we still have quite different behavior, and the initial capital stock clearly matters. So these are interesting findings as well. We just failed at manual experimentation to find an equilibrium, although we didn't try very hard. We might investigate that a little bit more thoroughly if we had more time, with a deeper thought about the structure of the model that's responsible for equilibrium in each of the individual stocks. Starting with this, going back to basics, the basic condition for equilibrium is that inflows plus outflows, or the net flow influencing the stock, have to sum to 0. And it may be possible to develop conditions for that to arise one at a time, or it maybe not. But in any case, we could pursue an analytic solution more formally, and we might get to something interesting. There's another option, which I won't pursue here, but leave as an exercise in the interest of time, which is to do it numerically. You can use the optimizer to discover equilibria by creating a payoff that penalizes changes in stocks, attempting to therefore to set them to 0, and then a control file that has access to the initial conditions for each of the stocks, run the model over a short horizon, optimize to minimize the initial changes in stocks, and you'll get equilibria. And this is the kind of thing you want to do in random multi-start mode so that you can discover multiple equilibria if there are any. Let's go back and look at a couple of the things that we happened to notice as we were playing around with the initial equilibrium, including that oscillation in pollution. So thinking about the big picture here, the thing that's of interest and concern to us as people is this big overshoot in population and capital that's happening. And incidentally, we should be concerned about that as a possible behavior mode for the global economy, but we shouldn't be concerned about the fact that it occurs for population more or less now, because this model is not making that kind of point prediction. It's making behavior mode predictions, but it's neither calibrated closely enough to data nor probably detailed enough to pick a year of population overshoot with any precision in time. And of course, the book and subsequent limits to growth and beyond the limits go into the details of that more considerably. So anyway, what makes that behavior mode occur, and what might make it go away? One strategy for understanding this is what we call feedback elimination. So if you look at the structure of the model, let's go back to our familiar pollution sector here. Pollution has its own feedback loop around pollution absorption, but it's also involved in some bigger feedback loops that go through capitals, through the capital ratio, and also population is impinging here, and so forth. So these create some loops that are hard to see. There are several strategies for getting at those. One is to use the loops tool and look at the feedback loops that actually exist through a given variable. So these are the loops that pass through population. Another would be to use the diagram tools to build up a diagram of particular loops of interest. And another is to essentially experimentally turn off various feedback loops. So there are several ways to do that. One is with an override. So I right-clicked pollution here, and I can override its normal behavior. The equivalent of that is to break the feedback loop in the equations. So if you don't have access to overrides in your version of vensim, you can just make temporary changes to equations using the equation tool. And one simple way to do it is to just multiply all the terms of the Stokes flow equation by a 0, and now pollution will be stuck at its initial value, as you can see on the graph here. Just don't forget to undo your changes, or you may inadvertently break your model, or at least save it under a new name that's clearly the experimental copy. Okay, so we're back. So we'll do this easy way using overrides. So I'm going to set pollution to a constant. And actually, before I do that, let me go back to my equilibrium view, because that's a more complete picture of the states of the model. So I'm going to hold pollution constant. I'll override it with a slider. And the default guess is 30 billion units, which is kind of high. So I'm going to set it to 1 billion, or 1E9 units. So that's near the initial pollution level and fairly small. And you'll notice that doesn't actually change the dynamics of the model very much. So clearly pollution was not high enough to drive the overshoot by itself. But population does grow somewhat larger and later. So what else could we change? Well, we could hold the capital agriculture fraction constant, or we could hold natural resources constant. So let's try that. I'll override that with a constant, and let me set this down to about the initial value here, 900 billion. So now you see population and capital are growing. So it appears that we've gotten rid of the overshoot dynamic by removing the resource constraints. And that's really not all that surprising. But then we have to think about what that means in the real world to do that, and what other concepts might exist in the real world that might be omitted from the model. But we should probably also verify this assumption that we've gotten rid of the overshoot mode. It may just be that we've moved it far into the future. So I might want to move final time out another 100 years. So I'm going to run to 2200 and see what happens. And it does look like we've made a persistent change. So initially I held pollution constant, then natural resources. What if I unconstrain pollution here? So I'm going to uncheck this box to remove the override. Now there's an interesting behavior. We have a population, capital, and pollution limit cycle. Actually, it involves the capital agriculture fraction as well. Or at least it appears to be some kind of limit cycle or lightly damped oscillation. So that's an interesting thing to explore. Question is, where does it come from? Oscillations are always a bit tricky because they have a tendency to involve everything in the model. So in this case, natural resources can't participate because it's overridden, but I can see that many other things in the model are oscillating alongside the pollution variable. So how can we trace that? Well, there are several strategies. One is we could just do some more feedback elimination. So for example, the capital agriculture fraction seems like a variable that's somehow not as fundamental as population and capital. So one question that seems reasonable to ask is whether that needs to participate in the oscillation. So I can override that with a constant, and I should set it down to something like 0.25 that's kind of typical of the model range. And what you see is that that state is not essential to the oscillation. It has a little bit of influence on the exact trajectory, although actually not a lot. So this is clearly not fundamental to the oscillation. So now we could either do more feedback elimination on the states, or we could start selectively looking at other things. So we could override capital, for example, and see what happens. And that's a little too big. So that's clearly implicated, at least. Let's remove that override. And presumably population is intrinsically involved as well. And indeed, that seems to be the case. So now there are more possibilities among the remaining three states. So there are other things we could do. One is we could just start playing around with the parameters of the model. So I'm going to move to the first control panel. And we can look at how does the birth rate influence that. And you can see that it changes the timing of things, but certainly the persistent mode doesn't go away. We could look at, say, and actually that was the initial birth rate pre-World War. So actually the birth rate does change the period of these oscillations. My guess would be that the death rate will do the same thing. Interestingly, not as big an effect on the period, but a bigger effect on the amplitude. So that's interesting, worth exploring further. And I could work my way through the other parameters in the model doing the same thing. And then the other thing I might do is consider the lookups. And lookups are basically a shorthand for a parameterized functional relationship. So I could look at one of those. So here's the pollution absorption time relationship that captures this effect of increasing pollution absorption time as sinks get saturated. And I could either add a parameter around this lookup to vary its effect, or I can just quickly flatten the lookup by editing it. So if I make all of these values 2 so that the pollution absorption time is more or less constant, I can see what happens. And it turns out that this matters. The oscillation goes away when I do this. So it appears that the sink saturation or sink poisoning dynamic is an important part of that oscillation as well. So that's yet another interesting piece of information about this model's behavior. Now let's shift gears a little bit. I'm going to close this lookup and stop the setup, get back to our base case, and we'll take a look at some other aspects of the model behavior and structure. So far we've been doing a lot of behavior tests and extreme condition tests manually by synthesim overrides or tweaks for equations, but it's often nice to be able to automate those so that you can accumulate a library of checks on model quality. We call these reality checks, and they're really sort of like supplemental data that can be automatically run to test a lot of different aspects of your model as you build it. So here's an example of one. Down at the bottom here you see the TI and RC variables. I've just named those to indicate their purpose. So TI is short for test input and RC is short for reality check. So let's take a look at that. This is a test input for no capital. So you'll notice the type of this variable is reality check and it's a test input. And the condition that this is going to impose is that capital goes to 0, so that's here, as a step function. So it'll come along until this parameter step check time, and then capital will be artificially forced to 0, and we'll see what happens. So once we impose that test input, then we check to see whether our reality checks are true. So one thing that we expect to be true if there's no capital is that there would then be no output and therefore no investment. So this is a constraint, so something that has to be true. It says that capital investment has to be 0 after the step occurs. So to run that, we just use the reality check button in the toolbar here, and we can select from a menu of reality checks if the model had a bunch of them. But I'm just going to hit test all. And you'll see that I got a report and a graph. So the report says the constraint reality check no investment was violated in 1951, which was the time the step was imposed. And you can see here why that is. So the red line is the constraint that is meant to be observed, and the blue line is the actual model behavior. So in other words, I forced capital to 0, and yet somehow miraculously I'm still getting non-zero capital investment after that occurred. So that's a problem with model structure. There's some sort of failure to observe conservation laws or something. And therefore, I'd like to look a little bit more deeply into this loop structure involving capital and investment. Capital investment in this model is really a decision, as is the fraction of capital that's allocated to agriculture. The tricky part is that in a global model, the decision is sort of delegated to millions of individuals, so it's an aggregate outcome of a lot of little decisions, whereas in a model of a single firm, there might be literally a monolithic decision to, say, build or not build an LNG terminal. So in a global model, the decisions are sometimes rather diffuse, but still there's an ideal that we would like to adhere to. And here's one statement of it from Peter Senge's thesis, which is that decisions ought to involve explicit stocks and flows. They ought to explicitly distinguish desired and actual states. So typically there's some kind of gap closing formulation where there's a desired inventory and an actual inventory, and the decision to produce product is driven by the difference between those states, for example. A decision should only use information that's actually available. So we could go back and look at the model structure and see what's available here. So in this case, the investment decision depends on population. Well, that's probably plausible. And on the material standard of living, that's plausible as well. So this model may be sort of a reasonable statement of at least some plausible information inputs to the investment decision. That's often not true in economic models, particularly optimization models, where the capital investment decision would explicitly include information about the future and about untried contingencies if the model is stochastic. And that is, of course, it's intended as a proxy for forward-thinking behavior on the part of agents, but real agents don't know the future. So it's philosophically a completely implausible or even impossible structure for decision making. And of course, in most situations, you would like the decision structure to reflect the way that real people actually implement the decision in practice, and the decision shouldn't blow up under a variety of extreme conditions that one might imagine. So certainly here we're failing at least on the last line, um, and would probably want to think more deeply about the implications of this for the behavior in the model. In the course of playing around with this model, we've now identified several potentially serious issues that ought to be investigated further. But it's really not a black or white situation. Any model is going to have limitations. So in part, the task here is to fix the problems that we find, or just toss out the model if it's really quite hopeless. But once we've identified, once we've repaired the major defects, we can use the model to draw conclusions. And as long as we respect the limitations, we don't take it into parts of the state space where we know that some of the more serious issues will be triggered. So as you make that transition, you shift to a mode more of trying to understand what's the outcome of the model, sort of which run is best and why, which is the title of or approximately the title of a nice paper, and start doing some sensitivity analysis to try and understand what a good decision in the model means. And when we create a good outcome, or a bad outcome, we'd always like to tie it back to feedback structure and understand how did the change I made change the gains of the loops or the state of the system in a way that led to a different outcome. So these are some of the things we might be thinking about. And ultimately, particularly once we have a fairly refined model and a lot of scenarios to evaluate, we can automate that by creating a payoff function that expresses the goal that we're interested in. And of course, there are questions always about whose goal is it and is it appropriate. And we can then turn the optimizer loose on this problem in a variety of ways. Here's one quick example. So I get into the simulation control. I go to the advanced tab. I've got a payoff definition here called quality of life. So quality of life is a derivative of the material standard of living and of pollution and food and crowding. So that's my goal. And I'm going to actually turn the optimizer loose to do an all constant sensitivity analysis. So I've actually turned the optimizer off, as you can see here. And instead I'm going to vary every constant in the model by 10% and see how much it affects quality of life. This is sort of a way of doing a mass filtering of all of the parameters to see where the leverage might be. Of course, the leverage might be in a structure that I don't have, so that's something I need to be mindful of as well. So I'm going to hit optimize, and that actually ran really fast. We could hardly see it because this is a small model. And my output is in a text file or a tab delimited file called with the run name and sort sense appended to it. And I'm actually going to open that in Excel just because it's a little cleaner to view. So here's my result. A list of parameters sorted in descending order of sensitivity on the outcome of quality of life, and then I can see the effect each one had. And actually it's handy to give these some conditional formatting. So I can see the big one is the quality of life normal. That's a trivial multiplier, kind of uninteresting. Next one is the capital investment rate. So that affects the growth rate of the economy. Then the normal food per capita, probably another sort of nuisance parameter. birth rates, death rates, and so on. So I could use this as a way to explore leverage in the model and maybe also to think about uh, what if there were time variation in these, or I constructed different kinds of decision rules that gave me some additional parameter flexibility. So there's a lot more you can do with this sort of optimization approach, but it's a very powerful way to try to maximize the outcome or create desirable behaviors in the model, exploring things automatically that you might not think of doing in a manual experiment in a control panel. And of course, that's yet another way to analyze your model, because the optimizer will ruthlessly exploit its weaknesses that you wouldn't necessarily think of, because your own behavior is constrained by what you think is practical for decisions. So this is also a very helpful way to make your model still more robust. So this is a deep topic. I encourage you to pursue it further by finding classic models and critiquing them on your own. It's fun, and you learn a lot about modeling from doing it. And as a byproduct, you get better decisions at the end of the day. Thanks for watching, and be sure to check out our other videos in the video library on vensim.com.